Okay, so far we assumed that the whole motivation for doing maximum likelihood was, hey, I did not know anything about the parameters before I started the experiment, right. Before I gathered the data I did not know anything about the parameters. Suppose I did know something about the parameters, right. So what could you know about the parameters? Let's stick with the coin tossing experiment. Give me something from the coin tossing experiment.
Fair.
Yeah, well, yeah, I know with a high probability it is fair. If you know it is fair or not, that's not prior information, that's insider trading. Okay. So with a very high probability, I think it's fair, right? So he hands me a coin. I mean, look at his face. I mean, obviously he's not going to cheat me, right? So so I'll assume it's a fair coin to begin with, right? So what I can do is I can have a prior probability of it being fair being very high, right? Now I can in fact think of having a Gaussian with a peak at 0.5 for my rho, right. I can think of having a probability of 0.5 for 0.5, right, for rho being 0.5. So there are two probabilities here now, right, do not get confused. There is a probability of the coin coming up heads and there is a probability of that being 0.5, okay, right. So that is the prior probability we are talking about here, and I am saying that I can think of it as a Gaussian, right. Are Gaussians a good idea? No, why not? Great. Negative probability is not only problem, it can be even greater than 1 also. I mean, either side is a problem, right. So what is a good distribution to do? Yes, you already seen that in your tutorials, probability tutorials. Beta distribution, right. The beta distribution is limited between 0 and 1. In fact, it seems to have been invented for putting priors on probabilities, right. In fact, it was. So so you can think of that as your prior, right. So I have some information about p theta, right. I want to use that in my optimization, right. So these are called right. So we looked at maximum likelihood or ML here. Now we are going to look at maximum a posteriori or map, right. So this is a priori information, right. This is prior information about theta and that is the posterior information about theta, right. But are we actually computing the posterior here? We do not know it, right. So we will have to see that. Anyway, so what we are interested in is finding out that theta that gives me the maximum posterior, right. So if you think about it, I do not have to actually compute the posterior to find out the theta that gives me the maximum posterior. Why? Because x is common, I can ignore that, I can only do an argmax on the numerator, I do not have to do the argmax on the denominator, right. So I do not actually have to compute the posterior. So as long as I have a convenient form of just dealing with the numerator, I am happy. right. So, I can just do the max over the numerator, and of course I can take the logarithm, right, because this is a nasty term because it has a product in it. So, I take the logarithm, convert that to summation, and basically do the max of this, right. So, there are a couple of things which I want to point out here. So, the one is, yeah, if you have some prior information you can use that, right. So, if you believe in the honesty of the person you can use 0.5, right, but there are other cases where I do not really have a prior information about what the true solution will be or what the true solution is, right, but I have some prior over what I want the true solution to be. Do you have cases like that? We tried to do this when we did ridge regression or when we did lasso, right. We wanted the parameters to be small. The way I achieved that was by putting a quadratic penalty, right. Instead of that, what I can do is I can say that, hey, I have this prior which gives very low probability to high values of the parameter, right. Right, I can make this prior, you know, all of you know about beta distribution. I can have all kinds of weird shapes to the beta distribution, right. That is the nice prior, right, the honest prior, right. So, it is a really honest prior, okay, and that is something like the L1 prior, L2 prior, sorry, right. So, the probability of the higher values beta being high is small, or rho, probability of rho being high is small, probability of rho being small is high, right. So, this is one way of thinking about enforcing a regularizer, right. Does it make sense? So, I can use the priors for enforcing my regularizer. I can say, no, do not give me things that have very high parameter value, I am interested in smaller parameter values. And if you, this is just about single parameters. If you want to talk about multidimensional case, you can also say that, hey, I will give you a low probability of having a solution which has more than 30% of the parameters non-zero. So, what will that enforce for me? Sparsity, right, that will enforce sparsity. So, the probability, so if I need to have, here is a question, suppose I really need to have my rho here, my rho is actually there, right, but I start off with a prior that looks like this. Will I reach my correct estimate for rho? Somebody said it depends, so I am happy. Depends on the amount of data I have, right. So, it depends on the amount of data I have. So, if you have an informative prior, great, the amount of data that you actually need is actually low, right. If your prior is correct, right, if you put the maximum probability on the right solution, the amount of data you need is low. But if you put the priors, the maximum weight on the priors on the wrong solutions, the amount of data you need is going to go up significantly, right, the amount of data you need is going to go up significantly. So, I made 2 points about priors, right. So, just remember, what are the 2 points? Priors can be used for regularization, okay. So, wrong priors need more data to correct, okay, and a completely bullheaded prior can never be corrected. right. So what is this? It is actually the beta distribution where I have written the normalizer in a slightly different format. You are used to seeing the normalizer as okay. So what is this called? That is the beta function. Okay, this whole thing is the beta distribution. Okay, so you actually have 3 betas here. So the beta distribution, okay, and the beta parameter, lowercase beta is a parameter, and then you have a beta function there. Okay. Okay, so the thing to note here is that your alpha and your beta parameters, right, almost act like as if you have seen heads and tails, right. So your alpha is just increasing the count of your heads, right, and the beta is increasing the count of your tails. Does that make sense? Right, alpha is just increasing the count of heads. So if I had actually done the experiment, I would have seen n1 heads, right, but I am assuming in addition I saw alpha minus 1 heads also, right. So if I am going to have a prior like this, right, can you imagine what would be the values of alpha and beta? Alpha will be less, beta will be more, right, because alpha adds to the heads, right. So rho would be higher. If alpha is larger, rho would be higher. So if I am going to skew it like this, so they should have a beta larger than alpha. You can start reasoning about all of these things just if you understand what is happening. So these things are sometimes called pseudo counts.